Cool. Hi, good evening. Well, thank you so much for having me. My name is Javier. I work at a company called Polar Signals, where we develop continuous profilers. And before that, I was working at Facebook on web infrastructure and performance, reliability, and developer infrastructure at different times. To be honest, personally, I don't develop C++, but I've been working on something that has quite a bit of overlap with how C++ works. I thought that it would be interesting to talk about it here because maybe some of you are aware of how stack unwinding works in CPP, but definitely I didn't know how this worked before, and I didn't know about all the interesting edge cases and interesting mechanisms that exist to make it work. So after talking to some people that have been developing on with C++ for a little while, they told me they didn't know about this, and I was like, okay, this could be like an interesting thing to discuss with the broader community. So, yeah, unwinding is this thing, right? That basically is about like walking up every frame that your program has at a certain point of its execution until you reach kind of the bottom frame. Let's say it's main, right? Even though it's not really main, but let's say it's main. And surprisingly, there is a lot of machinery for this to work properly, and we are really standing on the shoulders of giants. So. Something interesting here is that the talk is unwinding CPP, but in reality, this could be in pretty much, there's some exceptions in most native applications. Most of this is similar to, for example, how Rust does it. Go is a bit special, like many of the things that Go does. They have something similar, but custom. And Haskell does some weird stuff, but they follow something similar. But pretty much every other application every other like runtime or compiler that works basically produces an ELF executable in Linux, it uses a very similar approach. So first, let's talk about how stack unwinding was done. Well, first, why it's important, right? Like perhaps your application uses exceptions. Maybe you have banned them, like I think Google does, but perhaps you have exceptions, right? So at some point, these exceptions are going to be erased. So the stack is going to the stack is going to be walked until certain point, certain things are going to be executed, and but this process has to happen in some particular way. So turns out this is something that before the 90s it was solved by using something called frame pointers. So frame pointers work by inserting these yellow bits, which is called the prologue, before your actual body of your function, and then you have like the prologue, the epilogue at the end. So what it is doing basically, it's creating a linked list. It's pushing the current RBP, which is the frame pointer in x86, and then it's setting the RSP as the current RBP. So basically, if we want to traverse the stack at these points, what we need to do is traverse a linked list. So here you can see the contents of a process stack, assuming that it doesn't have any local variables. They will be in between, but doesn't really matter here. Where in the current executing frame, we have the saved RBP, and then we have the RIP, and then for every single frame, we have this pair, right? We have the saved RBP plus the saved instruction pointer for the previous frame. So as you can imagine, walking this is pretty cheap, right? We just need to dereference a couple of pointers as many times as frames we have. And this was great. But turns out, well, this is the algorithm that I mentioned. So you start with the current frame pointer, and you have some data structure that is some sort of list where this is some pseudocode. And basically, you need to dereference both the return address, which is in x86, it's 8 bytes ahead of the RBP. And you also need to dereference the frame pointer. Once frame pointer is 0, that means you have reached the bottom of the stack, so you need to stop. And you keep on appending the saved return address for every single of these frames. Basically, you're done after this process has finished. And you do it for X amount of iterations because you have no guarantees that the stack is correct. You can, of course, have extra heuristics for correctness, like, for example, ensuring that the RBP and return address that you're reading is within the limits of your stack. But basically, this is the general algorithm, and this is how most unwinders operate. So, of course, it depends on your on the CPU you have. But on x86, each L1 cache access is around 0.5 nanoseconds. And we only have 2 L1 accesses here per loop. So this should be pretty fast and efficient, right? There's only one thing that I want to mention here because I think it's very interesting, which is, well, they're fast, they're efficient, they're correct, except for assuming that they are generated for every single function in your program. But there is one particular case that is interesting to take into account and that not every single unwinder takes into account, which is what happens if you're collecting the stack trace exactly when this push instruction, basically when you're generating this linked list, is executing. So in that case, you won't get that current frame that is running. A lot of profilers and debuggers work around this by partially disassembling the code. And whenever they realize that there's a sequence of instructions, there is a push RBP and this move, then they will say, okay, I need to add the current IP as the current frame, because otherwise I will lose the currently executing frame in my stack trace. But besides this technicality, they're fast, they're efficient, and implementing them correctly is pretty easy. Fortunately, we have a lot of baggage, which is in 32 bits x86, we had 8 general purpose registers, which means that basically using one for the frame pointer was reducing this by quite a bit of a percentage. So the problem here, of course, is it introduces more pressure on the register allocator. So potentially variables will be pushed to the stack sooner. So compiler engineers came up with this idea of, okay, we can disable frame pointers, right? So this is, by the way, how most Linux distributions ship their software. And I will explain later why this causes so many problems for profiler and debugger authors. But basically, this option, the f-omit frame pointer, became super popular. And back then, this was really important because gaining one register, basically from having 7 registers to have 8, that's a pretty big win. It have like some big performance benefits, right? Nowadays, we have 16 general purpose registers in x86-64. And if you run ARM, like many of us do nowadays, in particular the Mac ARM CPUs, I don't remember how many registers they have, but I think it's something like 30 something. So this is not that much of a problem anymore. But unfortunately, like many other things, and in the C++ world, I think this is pretty much the case in many of the features, there's a lot of baggage. So yeah, so how things work without frame pointers, right? If you think about it, without frame pointers, the only way you will have to try to walk the stack will be to read the whole stack of your process and have some heuristics, trying to figure out if the values you're reading potentially could belong to, the RBP values you want to see, or the saved return addresses or not. But of course, this is a heuristic; it could fail, so you could get stacks that are not totally correct. So what happens, for example, in this case, right? When C++ exceptions that typically this is compiled without frame pointers, what happens if an exception is raised, or what happens in Rust, which uses the same mechanism if there is a panic? Again, many companies, for example, at Facebook, every single application runs with crash handlers. So whenever an application crashes, you get a nice stack trace that tells you exactly what happens. What was the signal delivered, and also exactly which lines of code were followed before the crash happens. And in general, like most of us use debuggers like GDB or LLDB and profilers. So they also have to do something to make things work without frame pointers. So the answer is DWARF. DWARF, for those of you that are not aware, because maybe you develop on Windows or Mac, but in Mac, I think it's also used. It's this specification on how to do a bunch of things. So it tells you information about programs in many ways, many different angles. So for example, you have type information. You know exactly for every single class, every single structure, what are the offsets, what is the size of every single type, and what are the types of every single field. We also have line information to be able to transform addresses to symbol names or class names and line numbers. And we have the other bit of information that is what we're going to talk about today, which is unwind information. So I'm going to start by showing you high level how this looks. And I will explain what this is because it looks a bit weird. So you can use readelf on Linux to read this data structure that is typically stored in the EH frame. It's .eh_frame section of ELF executables on Linux. And here I'm just dumping my systems libc. And basically what this is telling us is that this is like a function in our application. And this is what it's called the unwind table for this function. So we have 2 program counters on the left and on the right. Those are the the program counters where our function is covered in. So it starts in 29.3b0 and it ends in 29.417. And then every single of these rows tell us for every single instruction boundary how to recover registers. Again, registers can be pushed anywhere in the stack, and any register can potentially be pushed. The important things to know here is the first column is the CFA. CFA is just a fancy term to say what is the stack pointer value for the previous frame. So here it tells us if you fetch the current RSP and add 8, you will be able to find the previous frame's stack pointer. Then we have the RBX, which is basically the RBP, the frame pointer, which in some cases is U, which means undefined. The other bits mean that the C minus or C plus, it means that is an offset on the CFA. So it will be compute the CFA first, subtract 16, and you will get the value of RBP for the previous frame. And then we have the return address. The return address is, of course, super important for stack traces because it's the way we get the previous function that was being executed. So this information is super comprehensive, and hopefully it's well generated by your compiler. Otherwise you might run into a lot of troubles. But basically, something to know about this is that we have information per compile unit. For every single compile unit, that typically it's a file, we have information for every single function. And these are basically indicated by different data structures in DWARF Unwinding information, or CFI, as it's called. But this is the interesting bit here. I showed you like the representation of the table and how it looks and how you could manually unwind the stack if you wanted to. But let's talk a little bit about how this is implemented underneath. So this is a lot of fun because it's implemented as a bytecode. So we need a small VM to be able to interpret it. We have some good and some bad news. The good news is that most of the opcodes that we need to interpret, the result is a state machine. So that is good because we can produce this by using a stack machine. We don't need a Turing complete VM. And this has a bunch of benefits that some people really disagree with, but I really think that DWARF is a marvel of engineering, to be honest, because it has a very high compression rate and incredibly good space usage. So on disk is very, very compact. Just to give you an idea, I will tell about some custom format we've developed later on, but our format is twice as big as this. And we don't support any register. We only support 2 registers, while DWARF Unwinding information supports any register, any architecture, which is mind-blowing to me. So just to give you a hint, like some taste of some of the different opcodes. So for example, we have an opcode, doesn't matter the name, but I wrote it there in case you want to look into it later, which is the family of set location. There are several, but they don't matter. The other don't matter. But basically, this location is telling us we have a new instruction boundary. So there is a new assembly instruction that will be placed there. There is another one that is interesting here. It says push the current states into some stack. And of course, we have one that says retrieve the last saved state on the stack. And around 30 other opcodes that you have to implement if you want to be able to unwind stacks on C++ applications. But there is one that is a lot of fun, which are the expression type of opcodes, which as arguments, they have other opcodes, which is like a different type of VM, which turns out has to be Turing complete. So it can do arbitrary things such as, please fetch this register, dereference it, apply this arithmetic operation, and then this will be the previous frame stack pointer or whatever. So this is, of course, very interesting. And there's some researchers that have published this very cool paper, which basically, by modifying the DWARF Unwinding information, they were able to, well, inject some nasty code on your machine without any antivirus software or any other threat detection software being able to detect this, right? Because this is at a layer of abstraction that most people don't think about. So anyways, going back to C++, what actually happens when you raise a C++ exception? So as we know, like exceptions in C++ are zero cost. So basically, unless the exception itself is raised, you don't pay a price, right? Everything's free for you. But when you raise an exception, things are incredibly expensive. because we need to do this. This is typically done by live unwinds. Live unwind doesn't really mean anything anymore because there's LLVM's live unwind, there is libc's live unwind, there is GDB's live unwind. There's many implementations, so depending on what you're using, you'll be using a different library here. But the general way they work is the same. So first, it needs to find this unwind information. So there needs to be some sort of parser for ELF to find where these bytes live in memory. By the way, this ELF section is, I forgot the actual term right now, but it's always allocated in memory. It's enforced by the API. So it will always be present in memory. And so we need to find it. We need to parse this information. As we said before, there's information for every single compile unit. There's also information for every single function. So first, we need to find the right function. And as we saw before, we have the low program counter and the high program counter that covers each function. So we need to find the right one. If we are unlucky, which is most of the times, we need to do a linear search. If we are lucky, there is some acceleration tables called EHFrame HDR that allows us to binary search over this information. So once we find the right function, we need to generate, we need to evaluate these opcodes that I was talking about before that could include expressions. And once we have interpreted and evaluated the bytecode, we restore the register for the previous frame. And we keep on doing this over and over until some stop condition. They're well defined by the ABI. And of course, your compiler might decide not to follow it, but that's a big problem too. But anyways, it does these steps until you basically reach the bottom frame. So as you can see here, this is not just a couple of L1 misses. This is like this is a lot of work, right? It's a lot of work because also maybe in your company, you have decided that it's a good idea to use swap, which it is a good idea to use swap, even though it might seem that it's not. And perhaps part of your code that used to be in memory, now it's offloaded to ZSwap or to disk. And every single time you have an exception, if that code is called, which typically will be because exceptions are exceptional, you'll have to load that from secondary storage, right? Or from compressed memory. And we can talk about this more later, or if you have any questions, we can try to answer them. But let's talk a little bit about how perf does this, right? Because if you think about it, with frame pointers, the kernel has a frame pointer unwinder for user space. So it's just able to follow these pointers very easily. But in the case of not having them, which is the case for, as I said before, most applications written in C++ or Rust, what the kernel does is it copies the process stack every single time it takes a sample to user space. And then in user space, it uses live unwinds to be able to process this information and generate the stack traces, which is incredibly expensive. So this is kind of the reason why I know about this and I've learned about stack unwinding in C++ and Rust because I work building profilers, and the performance that we got with perf wasn't good enough. As I said, and we need to copy the user stack, let's say, for example, 100 times a second, which produces a lot of data, but also it's copied from your application to our profiler, which is a security problem, right? Perhaps you have some private key in your stack. So our approach has been to use BPF. BPF is a Linux technology that basically allows you to load, it's like a kernel extension, but only that it's a bit fancier and safer. It allows you to run arbitrary code in kernel context, only that it checks for safety. So you cannot do, for example, any kind of memory dereference, and your program has to be provably terminated. So some of the things that we wanted from this is that it's PMU based. That means that the CPU has some counter, and whenever this counter overflows, we can take a sample. Allows us to do system-wide profiling. So we set up these events once per core, and whenever they trigger, we grab a stack trace of this program, whichever the application is running, it's written in. Because this runs in kernel context, we can also grab kernel stacks, which is pretty interesting because sometimes your application, most of the work that it's doing is actually on the kernel. Like imagine like some sort of web server that is very well optimized. Ideally, most of the work will be done by the kernel, not by you. And then the stacks, we don't need to send the stacks individually to user space. We can do in-kernel aggregation. So we just keep counters and we bump them. And every couple seconds, we read all this information. We aggregate it. We generate some actual profile that we ship to some server. and we start from scratch. And of course, this also allows us to do other interesting things beyond CPU profiling or on CPU profiling, such as off CPU profiling, syscall tracing, and memory tracing that we're planning to do. In BPF, if you're familiar with BPF, implementing a VM there is pretty much impossible. So our approach has been to basically repurpose the dwarf and wine information into a format that is less compact in terms of size, but way more efficient in terms of CPU caches. So we basically store pretty much all the information we need from dwarf into 16 bytes. We're going to use less in the future because we have some information here that is only needed for ARM64. But basically, we're able to summarize all the information from dwarf that we need here. Of course, we are not able to support any kind of arbitrary expression, but luckily, there's two expressions that happen around 60% of the time, according to some statistics that we have gathered from open source software. So those ones are hard-coded. So just to give an idea of how the complexity of this increased, while you can implement a frame pointer unwinder in 10 lines of code, our unwinder is 700 lines of C code. And this totally excludes all the supporting code in user space that takes care of parsing these tables, evaluating them, converting them into this custom format, loading them into the kernel, and all the kernel and user space interactions, plus the tests. All that thing is completely removed from here. So this is just the unwinder itself, just to give you an idea of how complexity increases because of not having frame pointers. So anyways, I'm sorry to disappoint you. You wanted to hear more about C++ exceptions. I'm not the most qualified person to talk about this, but the idea is that all these mechanisms are used during exception handling, only that there's some extra mechanisms to, for example, understand what are the distractors that need to be run. There's this very good talk by Dave Watson that I really recommend that goes in depth into how all the CPP exception machinery works beyond the dwarf bit that 100% happens all the time. There's some links on some of the work we've been doing on our profiler. They go a little bit more in detail. We also gave a talk in FOSDEM, so feel free to check it out. And some conclusions that might be a bit obvious, but this thing that seems so obvious, and we throw exceptions all the time, under the hood is so much more complex than it seems. And in fact, because the C++ runtime and Rust runtime cannot rely on the existence of frame pointers, they actually, even if you enable frame pointers, they won't be used for unwinding. They will always be used. They will always use dwarf unwind information. Then thank compiler engineers, because maintaining this information across optimizations is kind of wild to me, how they do it and how it works so well. And perhaps even though this is not used for exception handling, I will totally encourage you to change your C flags after doing some benchmarking to see how this affects your application, because you really want this too. And the reason why you still want to disable the omission of frame pointers, so you really want to have frame pointers both for any function, but also for leaf functions, it's because if you run big C++ applications and they crash, perhaps you're familiar with trying to run them under GDB to see what happens. And sometimes GDB might take minutes. And I've been working with applications that are pretty large, and GDB might take up to 15 minutes to be able to start. So if you have frame pointers, you can definitely walk the stack in way less time, and you don't even need GDB to be able to do that. So yeah, that's all. And yeah, I'm happy to take any questions. Thank you.
Hi, thank you so much. So my question, you mentioned security. I presume that was about embedding into the binary is a problem, right? So they embedded into the binary, into the dwarf information, something that wasn't supposed to be there. How about, like, given how much of execution is happening, right? And how much, exception handling and all that executes different code, how much is a stack unwinding mechanisms or attack vector?
Well, first of all, I'm not a security expert, so I'm not sure how much of an attack vector it is. I really recommend that paper. It's quite readable and interesting. But definitely the part where some people run perf or similar profilers in production and then the stacks of your application are copied, like the whole stack, not just the stack trace. The stack of your process is copied to disk. I think that's definitely an attack vector, because if someone gets access to your machine, not only they get access to, for example, not only they get access to modify any application they have, but also they get access to the state of your processes that might not have otherwise because of permissions, right? So I think that it depends how you see this, right? If it's from the format itself, I think that the attacks they show in the paper are very interesting, but I'm not sure how difficult it will be in reality, because they will have to basically hack your compiler to be able to get that. But the attack where you're basically dumping the contents of your process stack to disk, and someone might be able to read it easily, like some of your a coworker might be able to check it and see like a private key or a password. I think that's more problematic than what the paper talks about. But that's my opinion. Again, I'm not a security expert.
I think you.
Any other questions?
Thank you. Awesome talk. How do you feel about Fedora, I think it was, who recently, in the most recent stable release, compiled everything with no omit frame pointer? Are you approve? Are you sad because it makes your business case weaker?
No. It doesn't make my business case weaker, because everything we have built is open source. So for me, I'll be more than happy to remove all the code I've been writing over the past 6 months and have only frame pointer and winding. I think that initiative is great, and I know that I used to work with the people that are trying to push for that. So I really like their behind this initiative. The only thing that I see here is that I think it's unfortunately impossible to get to a world where everybody uses frame pointers. Even if I can convince you all or every single Linux distribution to turn them on by default, it's going to take years until I can remove support for this in our profiler. So I'm 100% pro this, and in fact I haven't mentioned it here because but there is a couple of runtimes and a couple of companies that always use frame pointers. For example, Google and Facebook, everything has frame pointers. Every single Go application is compiled with frame pointers. Apple, all the software that runs on ARM64, if it doesn't have frame pointers, it doesn't run. And as far as I know, but they are mandatory by their ABI. They have their own kind of ABI extension, and they say, everything has to have frame pointers. So I think they're making the right choice, because I really care about reliability, like as a software engineer, and I really care about being able to debug your software when everything's on fire. And as I said before, when you have to spend minutes until you can get some tool to boot up to read all your massive data structures, and that perhaps there's something wrong there, it makes me not be able to sleep at night properly. So I'm 100% pro frame pointers, and I really hope that as many as you can turn them on. Talking about this, there's also some very interesting work by Oracle. They are working on this thing that used to be called CTF frame, and now it's called simple frame. So they're trying to build their alternative to DWARF Unwinding info, which is actually similar to our approach, only that theirs is more generic and works for more use cases. But there's a bunch of people right now working on this problem, because it is a big problem in the industry, like the lack of frame pointers and the way DWARF information works, even though it's so flexible, right? And it works for every single architecture, every single CPU out there, but it is so complex. Like when you have, like, I could show you later if you want, like there's some expressions that we have seen in the wild that have like 30 operations that involve like, fetch me this register, apply this offset, get me this other register, do a sort. It's like, this is ridiculous, right? But anyways, I'm 100% pro this.